Structural dynamics is a specialized field within structural engineering that focuses on analyzing the behavior of structures subjected to dynamic loads or forces that change over time. Unlike static loads, which remain constant, dynamic loads can include phenomena such as earthquakes, wind, waves, traffic, blasts, and vibrations from machinery. Key concepts in structural dynamics. Dynamic loads. These are time-varying forces that can be caused by environmental factors, for example, wind and earthquakes, or operational conditions, for example, machinery vibrations. Dynamic loads are characterized by their acceleration and frequency relative to the structure's natural frequency. Principles of motion. Structural dynamics is governed by Newton's second law of motion, F equals mass times acceleration, where the force acting on a structure equals its mass multiplied by its acceleration. Unlike static analysis, dynamic analysis incorporates inertia and damping effects alongside stiffness. Dynamic system components. Mass represents the matter in the structure, contributing inertia forces. Stiffness determines the structure's resistance to deformation. Damping accounts for energy dissipation due to internal resistance or external friction. Dynamic analysis techniques. Modal analysis identifies natural frequencies and mode shapes of structures. Time history analysis evaluates how structures respond over time to dynamic loads. Finite element methods are often used for complex structures. Structural dynamics is vital in designing resilient structures capable of withstanding dynamic forces. Common applications include earthquake engineering. Ensures buildings and infrastructure can endure seismic activity. Wind engineering. Studies the impact of wind on tall buildings, bridges, and towers. Machinery design. Addresses vibration control in equipment such as engine mounts. Infrastructure projects. Designs large-scale structures like dams and power plants to resist dynamic forces. The equation of motion for an Stoff system is the cornerstone of structural dynamics. It is expressed as the formula in the red box. This equation accounts for three components: inertial force, damping force, elastic restoring force. The natural frequency of a single degree of freedom, SDOF, system is the frequency at which the system will oscillate if it is given an initial disturbance and then allowed to vibrate freely. Essentially, it's the inherent tendency of a system to vibrate at a particular rate when disturbed, which is determined by its mass and stiffness. This frequency is a fundamental property of the Stoff system, reflecting its inherent tendency to vibrate. It's not related to any external forcing function, but rather the system's own characteristics. Damping is modeled using the term damping coefficient and speed of the system in the equation of motion. The damping ratio Ea zeta, zeta, determines whether the system is underdamped, critically damped, or overdamped. In free vibration, the following can be observed. Underdamped systems exhibit oscillatory decay. Critically damped systems return to equilibrium fastest without oscillation. Overdamped systems return slowly without oscillation.